Yeah.
Okay. Okay, great. So it's a great pleasure to have Carolyne Zhang from Harvard who will talk about on-siteable symmetries and symmetry-protected QCAs and beyond. Please take it away, Carolyne.
Yeah, thank you for this opportunity to speak here. Today I'll be talking about work that has been in progress with Michael Levin for many years now. But some of it has been talked about in other recent papers, but there will also be some new stuff. Um, and because this might be a bit more of a technical talk. So first I'll tell you the definitions I'm using for QCA, locality preserving unitaries, etc. And then I'll give you some motivation. So there's some interesting relations between the study of QCA and the study of these kinds of non-onsiteable symmetries and other topics such as SPT preparation. So I'll talk about those kinds of relations. And then I'll focus in on a particular locality preserving unitary that's quite interesting. And I'll use it as a key example to show some uh, new kinds of non-onsiteable symmetries that we can get, new kinds of indices and topological invariants, and their relation to these so-called lattice anomalies, which have been written about recently. And then the last part will be kind of not very rigorous. I'll just show you some things that we've recently been thinking about that we don't have concrete results about, but seem to indicate towards a richer structure. Um, okay, yeah, please ask questions throughout the talk. Um, so in the study of lattice models, it's interesting to study so-called locality preserving unitaries. And by locality preserving unitary, I just mean a unitary operator that takes local operators. So this is a 2D lattice system with a local operator OR, support on site R. And these kinds of unitaries conjugate local operators to nearby local operators. So it's marked by some operator spreading length L up to exponential tails. And in this context, I would like to distinguish between QCA and locality preserving unitary. So QCA, which have been studied quite deeply because their strict locality led to like stronger and more complete kind of mathematical approaches. Those are locality preserving unitaries that don't have tails. So if you conjugate a local unitary that's strictly local, these QCA will take you to another, a local operator that's strictly local will take you to another local operator with strict locality. But in this talk, we will allow for more general locality preserving unitaries. So this might take a strictly local operator to one that has tails, is mostly localized in some region, but can have some exponentially small support outside of that region. Um, so you might ask, what kinds of locality preserving unitaries are there? Certainly any unitary that's generated by a local Hamiltonian, so this is a time-ordered exponential of some local, possibly time-dependent Hamiltonian, any unitary of this form is locality preserving by Lieb-Robinson bounds. The dynamics stay mostly within a light cone. But not all locality preserving unitaries can be locally generated. So not all local dynamics can come from a local Hamiltonian. And the obstructions to local dynamics being generated have a rich kind of mathematical classification. So for example, in 1D, in one spatial dimension, the classification of locality preserving unitaries that are not locally generated are different kinds of translations. So you can show that you can kind of if you have a 1D translation, you can't generate that in finite time with a local Hamiltonian. This is opposed to in kind of continuous space where you can generate it by the momentum operator. But when you discretize space but make the time still continuous, then this becomes kind of a anomalous preserving unitary and that it can't be generated by a local Hamiltonian. So this was kind of discussed in mathematical rigor in this paper here. In 3 dimensions, 3 spatial dimensions, these kinds of locality preserving but not locally generated unitaries, um, a lot of them take the form of these kind of Walker-Wong entanglers, and that's discussed in this paper here. And I won't go into the detail of the full classification. Here's just some examples. And 1D, this is also the only dimension in which rigorous work has been done for systems with tails. So these, strictly speaking, are about QCA. In 1D, it was shown that the classification of locality preserving unitaries, which include these kinds of tails, is the same as for these strictly local unitaries. And that was proven in 2022. But in higher dimensions, the equivalence of kind of classification with and without tails has not been shown. Why do I call them anomalous locality preserving unitaries? Well, they have a similar structure to anomaly inflow in the quantum field theory context that many of you are familiar with. So even if a unitary that's locality preserving can't be generated, locally generated in the dimension that it is in, it can appear as effective boundary dynamics of a related higher dimensional system. So if you have a anomalous unitary in, say, 1D, it can appear as effective boundary dynamics of a 2D locally generated system, and in particular, a 2D so-called Floquet system. Why is this the case? Well, if you have an anomalous unitary in 1D, this means that this U carries some index. You can always tensor it with a unitary carrying the opposite index, and the pair of these two unitaries can be locally generated because these indices are additive under tensor product, and so this U tensor U opposite carries trivial index and it can be locally generated. And so
Question.
now in 2D,
Are you
yeah.
claiming, is this like completely proven, or is this just some intuition at this point? The fact that you can always realize
So
these in higher dimensions.
um, right. So this is saying that if you have U, then because this kind of indices form an abelian group, you can always cancel it by some other U. So this construction should be very general
Okay, so you're
of
saying this
the,
this rich
yeah,
classification that you alluded to takes the form of an index that can always be canceled?
right.
Okay, thanks.
And this is because in particular, you can always take U opposite to be U dagger. Um, and that will carry the opposite indices. Um, and so you can take this pair, and that will be locally generated. And what you can do is you can act this on strips of your 2D system. So you have U, U opposite U, U opposite U, U opposite. And this, of course, is locally generated because each of these pairs of strips is locally generated. And then in the next time step, you can act with U, U opposite with shifted by one of these kind of half strips. And then what you will do is you'll cancel everything in the bulk, but you'll be left with the boundary dynamics just given by U. And so this construction should always work to give you kind of a locally generated unitary in one higher dimension that corresponds to this anomalous unitary in the dimension itself. I will mention later that when you add symmetry to the problem, so you look at the classification of these anomalous unitaries in the presence of symmetry, then this is a broad class of these kinds of correspondences to bulk and boundary is unitaries that can pump SPTs to the boundary. Yeah.
There's a question by Nati. He just raised his hand.
Yeah.
Yeah.
Thank you. Is there a difference between the case where the extra dimension is in a continuum or on the lattice?
Yeah, so a lot of these kinds of indices are non-trivial in lattice systems. I wouldn't really know how to make sense of them in the continuum. And so um, all of this is about the lattice. So for example, this translation index is going to give anomalous unitary in the lattice system, and it has a bulk corresponding locally generated unitary. But in a continuum system, that unitary would be locally generated. Does that answer
So
your
I
question?
don't, well, you did answer the question, but I don't get the sign of the answer. Is it that you have more anomalies in when the bulk is continuous or more anomalies when the bulk is discrete? The boundary is discrete, I understand that, but the bulk, is there a difference between these two cases?
I wouldn't really know how to make sense of a commit. If I'm just setting anomalies in d dimensions, I wouldn't know how to make sense of mixing a lattice boundary with a continuum bulk. So here I'm always considering
No, no,
lattice.
I'm only talking about the direction of the bulk, not the bulk itself is still a lattice, but the additional direction is continuous.
Uh-huh.
So for example, there are many papers analyzing the Heisenberg chain in one dimension higher with the additional can be either on the lattice or the continuum.
Uh-huh. Um,
Well, if you don't know the answer, that's
yeah,
also fine.
I don't have not studied that case rigorously, but in all the cases I know of, it seems like it would not make a difference. Um, as long as this direction is discrete, like this direction along the boundary is discrete. But I will not make a hard answer there.
Thank you.
Also, in the bulk,
Sorry, people
there
have
is a
been raising their
structure.
hands, so if you could also raise your hand if you have a question. Sal.
Yeah, so if I understand, lattice translations in one spatial dimension would be an anomalous LPU from your definition. What's the Floquet system in one higher dimension that corresponds to lattice translations in that case?
Yeah, so there's this very simple flow case system where you can, for example, consider square lattice, where at time step one, you translate this way, time step two, you translate this way, time step three, you translate this way, time step four, you translate this way. And you can show that all of the translations cancel in the bulk, but along the boundary, you'll have a non-trivial translation operator. So I can, does that make sense? You can think of it as doing a bunch of like little translations and they cancel in the bulk.
Mhm.
And of course, because these are little, they can be generated by just like a unitary acting along here, but then they don't cancel on the boundary.
Yeah, that makes sense. So should I always think of the Floquet system as like pumping something onto the boundary from the bulk? Is that what that
Um,
does in time?
yeah. Also, if you want, I should mention that if you wanted to do it in the I mentioned here, you can always realize translation this way and translation backwards with a finite depth circuit. And then you can compose all these guys in the cancellation that I mentioned before. But yeah, then you can think of, so that's why I said in the context of kind of when you add symmetry, then these kinds of anomalous unitaries, a broad class of them are SPT entanglers. And then these kind of dynamics would be pumping the SPT to the boundary.
I see. Thank you.
Okay, Hanyu.
So in your argument, the bulk seems to have a Fourier structure. So, do you need this Fourier structure, or maybe you argue that the bulk is in some sense topological?
So here I just considered that there's not really a sense of topological. There's a different sense of topological here because we're not really talking about ground states. We're just talking about operators. And so it's not the same sense of topological as you might say in some ground state, this operator acts in the same way, is the same as some other operator. So here, all I assumed was that there is a lattice, and I wanted to show that there exists some unitary in one higher dimension that can be locally generated and give you this boundary dynamics.
Okay.
So yeah, does that answer your question?
Yes.
Okay. Yeah, so a lot of the intuition that people have about topology and gap ground states, some of it carries over and some of it doesn't quite carry over. So that's why there's like new indices beyond maybe invertible phases and stuff that people are used to from continuum field theory. Okay, thank you for all the questions. Yeah, so before I just talked about kind of anomalous locality preserving dynamics without symmetry. You can also, of course, ask what happens in the presence of symmetry. And in this work, we're only going to talk about in the presence of on-site kind of unitary finite, or yeah, on-site unitary symmetries, including finite groups, and we'll later study also U1. And so now your lattice system is equipped with a global zero form symmetry that is just a tensor product of unitary operators acting on each of the sites. And so locality preserving unitary is symmetric if it commutes with all of the symmetry operators. And we can also define a symmetric locally generated unitary, which is generated by a Hamiltonian that is symmetric within this entire from 0 to capital T. So this is some unitary that is symmetric as a whole, but it might not be possible to generate this unitary with local symmetric pieces. So now the classification problem is like unitaries that are locality preserving and are symmetric as a whole, modulo those that are generated by symmetric local pieces. And we say that these two unitaries are equivalent together if they just differ by one of these kinds of trivial, locally symmetric dynamics. So let me tell you what are some of the interesting structures that one encounters when studying these kinds of locality preserving unitaries in QCA. One is that there's some interesting mathematical structure. So for example, I mentioned that in 3D, the classification of these QCA is closely related to width classes. And the idea is that the non-trivial ones sort of pump topological orders with non-trivial that are not equivalent to the vacuum to the boundary. And so there's an interesting kind of correspondence or between these kinds of QCA and width classes of in 2D, in two spatial dimensions. There's also an interesting relation to state preparation. So for example, if I have a SPT ground state and I want to prepare it from the trivial product state, symmetric product state, then we know that because it's possible to prepare this with symmetry breaking dynamics, because we know that SPT is short range entangled. So you should be able to get to an SPT. What I mean is like this SPT is equal to U on the product state for some locally generated U. However, you will have to break the symmetry. U has to break the symmetry because this SPT is a different class from the trivial state if you preserve the symmetry. So what that means is for a broad class of SPTs, you can get it from the trivial state, so psi SPT. You can get it from the trivial state by locality preserving unitary that is symmetric as a whole. So U commutes with the symmetry as a whole, but it can't be broken into local symmetric gates. And so a broad class of these kind of symmetry protected locality preserving unitary also have correspondence to the classification of SPTs. And then you can construct indices for these kinds of equivalence classes of symmetric unitaries that are built off of indices that people know for SPTs. As I mentioned before, there's a relation to Floquet systems or periodically driven systems in one higher dimension. I kind of just said that there's a correspondence between LPUs in one dimension and locally generated ones in one higher dimension, but it turns out that those locally generated ones also have a nice structure. So this is kind of the four-step swap circuit with the translation and the boundary that I tried to illustrate to Sal. And with symmetry, these are the one higher dimensional are SPT pumps. And there's also an interesting relation to the classification of lower dimensional kind of non-onsiteable symmetries, or so-called lattice anomalies, that was discussed in these two recent papers. In particular, these two recent papers studied index H2 of G with coefficients in the positive rational numbers. And these kind of described, in these papers, they were studied in the context of 2D, 2 plus 1D non-onsiteable symmetries. But the way that we actually constructed our examples was by starting off by constructing a QCA in 3 plus 1D and then deriving the symmetry from that. So let me, and I should also mention that sometimes these kinds of unitaries, you can write down nice indices for them. So this is a SPT entangler in 1 plus 1D, and this U is an SPT entangler in 1 plus 1D, and there's a very nice way to compute this cohomology invariant from this U. This U is an SPT entangler in 1 plus 1D, in this very nice closed form equation that just takes as input this QCA and some on-site symmetry operators. And so given a generic SPT state is typically quite hard to compute its SPT invariance in generality, but if you're given the path to the SPT state from the trivial state, then it can be quite straightforward to compute these invariants.
I have a question.
So yeah.
So you mentioned that LPUs relate to Witt classes. Is it known what the anomaly of an LPU, how the anomaly of an LPU is related to the Witt class application?
Yeah, good question. So the way that people argue for the non-triviality of these QCA, they just assumed in this kind of studies that the unitaries are strict locality preserving. So the way that people argue for the non-triviality is that if the unitary entangles a Walker-Wong model with boundary topological order that has say chiral central charge, then if you assume that the unitary was actually a finite depth circuit, you would obtain a contradiction because you would find that there exists commuting projector models, basically, that realize in 2D that realize topological order with chiral central charge. And so the idea is that this unitaries in 3D that are trivial QCA can only cannot pump kind of non-invertible phases with boundary chiral center charge, or more generally
Mm.
non-invertible phases with non-gappable boundaries, because
I,
we believe that these kinds of topological orders with ungappable boundaries don't have commuting projector realizations.
I see. So the anomalous ones can pump these chiral TOs, but they don't necessarily pump them, or do they always pump them?
All of the ones that we know of have this pumping
I
of,
see.
yeah, exactly.
Okay, thank you.
But
I
I
think
don't think
there's
that there's a rigorous kind of complete that there's a rigorous statement that that's complete classification in 3D.
Okay,
I
thanks.
think there's a counterexample. The U1 level 2 times U1 level -4. That one is also non-chiral but anomalous.
Yeah, but here that's still with non-trivial, right? Because it doesn't have a gappable boundary.
Right, but it's
So I'm
non-chiral.
including that here.
I see.
Okay. Um, okay. Yeah, I could say more, but I think that's the basic intuition that those QCA are non-trivial if like commuting projector models can't realize topological orders with ungappable boundaries. All of this is also in the context of bosonic systems, so there might be other things in fermionic systems. Let me kind of also say some words about GQCA and lower dimensional G reps. Because, for example, this is how we were able to construct these examples of symmetries with non-trivial H2 class in 2D that are non-onsiteable but admit trivially symmetric states. So the idea is that suppose that you have a G LPU. So that means that you have some representation of G on your lattice system. That's just kind of a tensor product of U's on each of the sites. And your unitary or QCA commutes with that symmetry. What that means is that if you restrict, so this is just saying that it commutes with the symmetry. So if you restrict this UG to a region, so let's suppose we're in 2D, we can restrict it to this large disk. So we can just take the product of the URs that are within this disk. Then if you conjugate with this QCA, what you find is because this unitary is locality preserving and it commutes with the global symmetry, it can only modify this restricted symmetry operator by something along the boundary. And so now we can construct a lower dimensional representation of this symmetry. What I can do is I can multiply this guy with UGAN. So AN is just going to cancel the action. It's kind of the restricted symmetry operator on a slightly smaller disk. So this will cancel the bulk action and it will leave me with a lower D-1 dimensional operator. And it will take some steps, but you can show that this actually forms a representation of G. So WGWH is equal to WGH. Yes, Hanyu? Hanyu, you can, what's your question?
What happens if we do not use A in, but only use A?
Then it's harder to show that it forms a representation of G. So that's why I'm using A in.
Also, maybe you have a typo that you only write UG but not UGA.
Oh yeah, sorry, this should be UGA. Okay, thanks.
Okay.
But if you do this, use this AN, then it's pretty straightforward to show that this actually forms a representation of G.
Personally, I really hope it can be UGA. And if we do not use A in, then I can get a complete formula for all dimensions.
Yeah, maybe we can talk about that. I feel like that should also be possible for AN because these should give you the same kinds of, they should just differ by some, they should be equivalent representations of G if having A here does give you a representation of G. But if you have A here, because these guys, this factor and this factor don't commute with each other, it's hard to, in general, doesn't appear that it should be a representation of G.
Okay, thank you.
Okay, thanks. Okay, so one can show that this actually forms a representation of G. Importantly, it's not too hard to show that if these are equivalent to each other, meaning they differ by a G locally generated unitary, then their corresponding lower dimensional representations differ also by this V, which is a locally generated unitary that's G-symmetric supported near the boundary of A. Okay, so that means that if these two QCA are equivalent to each other, then their boundary representations are certainly equivalent to each other. The converse is not necessarily true, but then we can say if we find boundary representations of a symmetry that are non-equivalent to each other, then that certainly allows us to say that their corresponding U's are inequivalent to each other. And so in the context of these GLPUs that are SPT entanglers, this construction just gives you the boundary anomalous representation of the symmetry. So you have an SPT entangler in 2D, and this construction will give you a 1 plus 1D kind of anomalous representation of the symmetry if this U is a non-trivial SPT entangler. It's why do I say that this converse, we can show if these QCA are equivalent, then their boundary reps are equivalent, but we can't quite show that if the boundary reps are equivalent, then the QCA are equivalent. One reason why one might hypothesize that this is not true is we typically define equivalence of representations of the symmetry with stable equivalence, meaning we allow tensoring in with ancilla degrees of freedom, and we also allow a rotation by a general locality preserving unitary. I should have written general LPU here. So we don't require this V to respect any symmetry. Because the anomaly is kind of detected in the fusion of these restricted symmetry operators, and the fusion just cares if these are related by a local unitary, doesn't have to respect any kind of on-site symmetry. And so if we define equivalence of representation of symmetry in this kind of more general sense, then I will show examples later in this talk where it appears that we have boundary representations that can be made equivalent, but their bulk QCA are inequivalent.
Does V have to be finite depth here?
No. So
Okay.
when we get the V from equivalent Qs, it is finite depth. But if we are just trying to define equivalent representations of a symmetry, then V just needs to be a locality preserving unitary.
Okay, thanks.
Thanks. Okay, so with all of those kind of definitions and preliminaries at hand, now we can look at the general classification. I can always split the classification, and we'll only be studying locality preserving unitaries with symmetry. So we're gonna assume that if you break the symmetry, you can always locally generate these guys, but they're just protected by the symmetry. In this context, we can always divide up the classification into kind of SBT entanglers and those that are beyond SBT entanglers. And on this side, we kind of have a more systematic construction in all dimensions. But on this side, we just have some examples. So this side is very much not complete. And today I'll be talking about this particular kind of beyond SBT U1 QCA in 3+1D. Okay, the basic idea of the action of this unitary is, I should mention that this is all in the context of fermionic systems, actually. So previously, a lot of what I said was about bosonic systems, but there are analogous statements about fermionic systems. The unitary that I'm going to talk about today is particularly nice because there's kind of free fermion constructions. So we'll be working in a fermionic system. And so the action of this unitary is, it is, again, a pump. So it takes many body Slater determinant state. So you can think of this as the fermionic states in the low space of this 3D system are completely filled. And what it does is it deposits kind of a Chern insulator at the boundary of the state. So it takes you from a trivial state that's filled in the lower half space to one where it has a Chern insulator at the boundary here. So that's the intuitive idea of what it does. For simplicity, let's first work in a single particle setting. So in a single particle setting, you just have the operators that act on the system have matrix elements indexed by the sites. Because it's a single particle setting, that means that kind of U1 particle number conservation is automatically preserved. So in this context, this U1 QCA I'm going to talk about is really just a QCA. It's not locally generated at all because you can't break the U1 symmetry. So what we have is just a 3D system, and you can think about it as a 3D cubic lattice, for example. And we're going to have 3 sites per unit cell. So that will give rise to, in momentum space, that will give rise to 3 bands. It will be useful to index kind of unit cells by R, which tells you the X and Y location, and RZ, which tells you the plane, the Z location. And then what you can do is for each layer in your 3D system, so we can mostly think about kind of being in momentum space in the X, Y directions, but staying in real space for the Z direction. So each layer in the Z direction has three bands, and we can write P plus, P minus, and P0 to denote churn plus band, churn minus one band, and churn zero band. So these are just projectors that live in this plane that project onto a churn plus band, churn minus band, churn zero. So this gives you kind of a trivial kind of integer quantum Hall state with a plus one churn number or plus one Hall conductance. And these are orthogonal and they are complete. So if you add all these guys together, that's just a projector into the fermionic states in this layer. And so what this unitary does, it basically translates the churn minus states and it keeps them the same. It translates the churn plus states up and the churn zero states down. And the reason why we want this translation up and down is to make sure that there's no net translation of operators. So the GMVW, kind of the translation index in the z direction is trivial, but you're still kind of pumping chirality. And so what you can show is that if you have the projector into the lower half space, then what this unitary does is it commutes with the projector into all of space, but if you conjugate the projector into the lower half space, then it modifies it near the z equals 0 plane, and it modifies it by a churn one band. And so this unitary is strictly locality preserving in the z direction. It kind of just pumps operators in one unit cell in the z direction. But what you can show is that it cannot be strictly locality preserving in the x and y directions. And the reason is projectors onto trivial bands can be made strictly local, meaning this is the projector and it's going to be a quasi-local unit Hermitian matrix. But in the case where this is a projector onto a trivial band, this matrix elements can actually end far enough away from the diagonal. But there's some rigorous mathematical theorems that say that if your churn number is non-trivial, then these bands cannot, projectors cannot be made strictly local. So there must be some decay away from the diagonal. That decay can be small and exponentially small, but it has to be there. Okay, so this is a distinction between trivial and non-trivial churn bands and projectors onto them. I should mention that this is not the same as whether or not a non-trivial churn band can be one-earized. So whether or not there exists exponentially localized Wannier functions for non-trivial churn bands. This is kind of an independent result, and I can say more if people are confused about that. But all we need for this talk is that if you have a projector onto a non-trivial churn band, then the matrix elements have to be cannot be strictly local, cannot be finite range. So what that means is that this boundary projector that you get by taking this PZ, conjugating it by this QCA, and then subtracting out the lower half space. This guy is supported near the RZ equals 0 plane and is local, so it's exponentially decaying in the x and y directions. You can also show that it's a projector. That takes a couple lines. And we can come up with an invariant. So this is just going to be the churn number of this boundary projector. And we can show that this, so okay, this is just the usual formula for the churn number of a two-dimensional projector. And you can show that if the two QCA are equivalent to each other, then you can show that if these two churn numbers are the same, then the QCA are equivalent to each other. So that means that all we need to do is construct an example of a U such that the C of U is non-trivial. We know that C of U is 0 for the trivial QCA. So that if we find one such that C of U is non-trivial, then that means that it's a non-trivial QCA. So in particular, this UC, because it pumps a churn one band, is a non-trivial QCA. It's not locally generated. And also, as I mentioned, because of these tails in the x and y direction, it is not this UC cannot even be written as a QCA. It has to be a locally generated, locality preserving unitary that's not a QCA. So this would not be found if you were just looking at strict locality preserving unitaries. You would have to allow for these tails. It takes some work, but you can also show that there's other formulations of this invariant. For example, if you just want to write it in terms of the this LPU instead of the boundary projector, then there's this winding invariant that naturally gives you kind of a map from T3 to S3. But this was studied in other contexts, not necessarily looking at 3 plus 1D anomalous unitaries. Okay, so how do we show that C of WU equals C of U for W kind of a locally generated unitary? So we want to show that if these are differing by, if these guys are equivalent locality preserving unitaries, then this invariant is the same. If you have W written in this form, you can always decompose it as some action near the boundary, near the z equals 0 plane, and the action elsewhere. So as long as it's written as time evolution of a local Hamiltonian, you can always decompose it as this way. So W boundaries supported strictly in this region near RZ equals 0. And then what you can do is you can write, so I've written W here, but the z bar in this equation commutes with P z bar. So you can commute it through and they cancel. So all you're left with is this W boundary acting on z bar. And what you can do is you can choose this region psi to be sufficiently large such that it commutes with this projector into RZ is less than minus chi. And then you can show that all you've done is conjugated the boundary projector by a locally generated unitary. And because the Chern number is invariant under conjugation by a locality preserving unitary, then this Chern number is always the same. And so this is a pretty straightforward proof that if these are related by a locally generated unitary, then this index is the same for those two unitaries. And so that immediately implies that our UC is a non-trivial QCA because the index is different from that of the trivial unitary. Okay, then there is a straightforward generalization of this to the many-body setting. So now we have these fermion creation operators, and we can fill many fermion states. So we're out of the single particle setting. It's still non-interacting, but many bodies because we can fill many fermionic states in the Fock space. And so there's an analogous kind of action unitary in this many-body setting that pumps Hall conductance to the boundary. So now we have a global charge, which is just the particle number. And this UC will commute with the global charge, but it cannot be generated by a Hamiltonian where each term commutes with the global charge, we will show. So yeah, this UC in the many-body setting commutes with the global charge, which is just the particle number. And we can define a many-body invariant that's quite similar to our single particle invariant. So you can define a many-body invariant that I will call H boundary, that is the analogous object to the single particle boundary projector that carries a Chern number. This H boundary will have a ground state that carries Hall conductance in the case where this is a non-trivial QCA. So you can construct this H boundary using the QCA, U1 QCA, and you can show that it's supported near this RZ equal plane. It's local in the X and Y directions. You can show that it has integer spectrum because these Qs have integer spectrum, and you can show that this guy commutes with this, and so this whole composite operator has integer spectrum. And under some assumptions, it has a unique ground state that has a non-trivial Hall conductance. And so now you can just define a similar kind of invariant for that we had, which was the Chern number of the boundary projector. Here, we're going to have the Hall conductance of the ground state. So this should be sigma H of H boundary, sorry. H boundary, okay. Oh, sorry, P boundary is the ground state projector of H boundary, so that's correct. Okay. So there is a similar argument to this single particle case that this kind of invariants are equal to each other if the unitaries are equivalent to each other as U1 QCA, meaning they only differ by a U1 symmetric locally generated unitary. And so this immediately shows that this U that we've constructed in this way that pumps Hall conductance is not locally generated in a U1 symmetric way. And even though the unitary you constructed is non-interacting, this invariant should hold as a general property of interacting systems as well. Okay, I mentioned that this is a U1 locally generated unitary, non-trivial locality preserving unitary. But there is a way to generate it as finite time evolution of a local Hamiltonian as long as we break the U1 symmetry explicitly. How do we see that? Well, we can take these operators that create momentum space eigenstates of these that fill these kind of Chern bands. And what we can do is we can write this U1 QCA as a product of two unitaries. The first one performs the swap between the Chern plus and Chern zero band and then in a single RZ layer. And then in the second step, this U2, it performs a swap between Chern plus and zero band layers between these RZ layers. Okay, so these are both, you can just think of these two steps as a bunch of swap operators where you're swapping the fermionic states. The problem is that this is a momentum space. So if we Fourier transform everything into real space, we know that these are not going to be local in real space because the Fourier transform of these momentum space modes are going to be non-local if this is a non-trivial Chern band. So we can perform this swap, but it's going to be completely non-local because Chern bands don't have localized binding functions. So the momentum space eigenstates, when you Fourier transform them into real space, those creation operators are going to be non-local. So then the idea is that we can do a U1 symmetry breaking construction by spanning this non-trivial Chern band by creation operators that mix the naive fermionic creation and annihilation operators. All we need to do is span this Chern band with a complete set of states. So we can use these other fermionic operators. And if these B's are translated upwards, because these D's can always be written as linear combinations B's and B daggers, these D's are also translated upward. Okay, so that means that instead of using these original D's, which are just Fourier transforms of the momentum space modes, we'll use these instead that create these Bogoliubov quasi-particles. So these are going to explicitly break the U1 symmetry because they combine the creation and annihilation operators, so they don't conserve particle number. But the short story is that once we use these B's, we can actually write these U1s and U2s that still have the same action as on the previous slide. So they still do this translation of the Chern 1 band up and Chern 0 band down, but now they're actually local. But to make them local, we have explicitly broken symmetry. So now this gives you a U1 symmetry breaking construction for this non-trivial U1 QCA. Right, so the idea is that we have fermionic quasi-particles and we have BDG particles in this Chern plus band, and we just swap them to move this guy up and this guy down. Okay, so all that is in the context of free fermion systems. This gives you a non-onsite representation of U1 in 2 dimensions. And this is because, as I mentioned before, these Chern plus and this Chern plus projector can't be made kind of on-site. Now, if we break this U1 to Zn, then that will give us something familiar. So as I mentioned in the paper by Wilbur and Michael and Wenjie and I, and also by Dominic Else and others, they we're looking at these discrete symmetries, these finite symmetries classified by H2 of G with coefficients in the positive rationals. And those have the property that if you have a Zn symmetry, say, and you take it to the nth power for a restricted region, then that gives you a translation along the boundary. So you can see this as well. What you can show is that if you take this U1 symmetry in 2D and you restrict it to a patch, and you do e to the 2 pi I h boundary restricted to a patch, then you'll also get a translation along the boundary. And so on any closed manifold, of course, UG to the n, which is just 2 pi I h boundary, will give you 1. But when you restrict it to a region with a boundary, then you get a translation along the 1D boundary. So breaking this U1 down to Zn gives you examples of these Zn non-onsiteable symmetries that we had in those papers. So in this case, we have a fermionic system, so it's a bit subtle. The n equals 2 cases gives you an onsiteable Z2 symmetry, because even though the U1 symmetry breaking construction that I told you about, it breaks the U1 symmetry, but it preserves Z2F, because it has these BDG quasi-particles that break U1, but still preserve fermion parity. But for n is greater than 2, this gives examples of Zn symmetries that have a non-trivial H2 class. In fermionic systems, we have to replace this Q plus by Q plus appended by square root of 2. So this is positive rational numbers up to some factor of square root 2. So to explain a bit further, suppose that I had the H boundary that was generated by the U1 QCA I mentioned previously, and then I break U1 down to Z2. That will give me a unitary such that UG square is a translation along the boundary if I restricted this H boundary to a region. But if I have a Z2 symmetry with UG square equals translation along the boundary, I can always remove this by doing a different truncation where I multiply by a Majorana translation that cancels out this resulting unit complex fermion translation. And so if I break U1 down to Z2, then this does not give me a non-onsiteable symmetry. However, if I break it down to, say, Z4, then I can't remove this boundary translation by choosing a truncation of UG to this region, by choosing some different truncation of UG. So then this is not trivialized by a different choice of co-boundary. And so this gives me a non-onsiteable Zn symmetry in fermionic Zn symmetry in 2D, 2 plus 1D. Okay, so this is kind of the natural generalization of those Zn symmetries to U1. One interesting thing is that there is actually kind of a subtle difference between these kinds of anomalous unitaries and Thouless pumps. So so here I talked about pumping the churn insulator. And you can ask, can I similarly pump a P plus IP superconductor? And so we can just use the same unitary action, but it acts by, I will replace the fermion creation operators by these Majorana operators instead. So you can ask, does there exist a unitary that pumps P plus IP superconductor in the sense that it takes this Majorana operator to this other Majorana operator where we've translated certain states up and certain states down, the plus band up and the 0 band down. The problem with Majorana operators are that gamma equals gamma dagger. So you need that to be preserved after you've conjugated it by this unitary. And so what that means is that this guy needs to be equal to its dagger. And these projectors are Hermitian. So if they're also real because they're equal to their star, then they're symmetric and they can't describe a projector onto a non-trivial churn band. And so at least this naive construction that we used for fermionic systems to pump churn insulator cannot pump P plus IP superconductor. On the other hand, there's a concept known as Thales pump where you can pump invertible phases. And the idea is that you can just kind of entangle P plus IP superconductor with P minus IP superconductor, P plus IP superconductor with P minus IP superconductor, etc. And so there's kind of a construction similar to what I gave to give the anomalous unitary at the boundary of a locally generated unitary to show that you can always pump invertible phases in one higher dimension. So this is an example where those two classifications differ. So the classification of Thales pump differs from these classification of these anomalous unitaries, at least under this construction. And it's actually not surprising because the intuition for how we were able to get this anomalous unitary in 3 plus 1D is it comes actually from a 4D Chern insulator. So if you have a 4 plus 1D Chern insulator is classified by Z, and you can show that the projector onto a state with a band with a non-trivial second Chern number, that will help us construct a 3D locality preserving unitary. But if you look at class D, which is the symmetry class of the P plus IP superconductor, that classification is trivial. So that indicates that there's no anomalous kind of 3D unitary that pumps P plus IP superconductor.
I have a quick question. Is it possible that the classification of one is a subgroup of the other?
The classification of what is a subgroup of what? Sorry.
So I thought you were saying that not all pumps correspond to these anomalous LPUs. Is it possible that the classification of anomalous LPUs is a subgroup of the classification of these pumps?
Yeah, I would say that the classification of these Thales pumps is a bit different from the classification of these LPUs because the LPU just shifts in this spatial dimension. So it takes the Z and it shifts it to 3. So that means that in 3D, there's like Z classification in the non-interacting case. And here in 3D, there's 0 because in 4D, there's a 0 classification so 4D, there's a 0 classification, trivial classification of states. So in 3D, there's a trivial classification of these QCA. And on the other hand, Thales pump is more like going diagonally because when you go to what a Thales pump does is it pumps an invertible state. And so what it maps you from the classification of like gapped phases in D dimensions to paths to loops of gap phases in D plus 1 dimension, right? So that means that you're going up in dimension, but you're also going up in the number of parameters you have in your parameterized system. So that's more like actually moving diagonally. So that's why this classification always coincides with this classification. At least in this free fermion setting. In the interacting case, I think it's also a little bit different depending on the symmetries.
Okay.
I can say more, but yeah.
Okay.
Okay. So now let me get into some of the more messy stuff where we don't have we don't fully understand everything, but let me just tell you some thoughts. And previously we just had the charge is just literally the particle number. And so each fermion carries unit charge. But you can ask, what if I have different flavors of fermions carrying different charges? And I'm just going to restrict to odd integer charges because we want e to the pi iq to still equal fermion parity. And so now I can construct a more general charge which assigns different charges to different flavors of fermions. And now we can construct, using a similar approach to before, we can construct these U1 QCA that give me this boundary non-onsite U1 symmetry. And using the construction that I had earlier, you can choose these different QSs, and you can also choose these different nu S's at your will. And this H boundary will still be quasi-local, it will still have integer spectrum, and it will still commute with kind of an on-site U1 symmetry in the 2 dimensions near the RZ equals 0 plane. Now, okay, considering this operator, there are many different kinds of quantities you can associate it with it. One is the GMVW index of this restricted 2D symmetry operator. So as I mentioned before, for the turn pump, this if you exponentiate e to the 2 pi I h boundary restricted to a disk, then it will give you a translation at the boundary of the disk. Now you can, so you can, for this general kind of boundary representation of U1, when you, because this has integer spectrum, if you raise it to the 2 pi I, then we know that on any closed manifold, it has to be just because this has integer spectrum. But when you truncate it to a region and then you exponentiate it, you might get some operator along the boundary of that region. So the GMVW index of that boundary unitary will be given by sum over S of QS nu S. You can also ask, what is the chiral charge of the ground state of this guy? And that's just sum over S of nu S. These are the Chern numbers of this projector. You can also ask, what's the Hall conductance of the ground state of H boundary? And that's sum over S QS squared nu S. And then there's a different quantity that I won't get too much into, but it's invariant classifying U1 symmetric unitary loops. And because this is integer spectrum Hamiltonian, as you take e to the 2 pi I, h t, and you ramp t from 0 to 2 pi, that gives you a loop in the space of U1 symmetric unitaries. And so there's a invariant that one can associate with loops of U1 symmetric unitaries, and that's this guy that's discussed in this paper here. So there's all of these kinds of quantities you can associate with this boundary non-onsite representation of U1. And we believe that this is an obstruction to making the U1 symmetry on-site. This is the one that, if you break it down to Zn, that gives us the H2 index that had been discussed in previous papers. So this we're pretty confident in. The chiral central charge of the ground state of H boundary, if this is non-trivial, that means that this operator has an eigenstate that can't be transformed into kind of a trivial product state with a local unitary, because this ground state can be transformed into a product state with a local unitary. So this seems like it's also an obstruction to making this guy on-site. This Hall conductance of the ground state of H boundary does not seem to be an obstruction to making this guy on-site, because if this H boundary carries non-trivial Hall conductance, that does not preclude transforming the ground state into a product state with a U1 symmetry breaking unitary. And when we define kind of equivalence classes of representations of a symmetry, as we discussed earlier, Sal had that question, we don't restrict the unitary transformation to respect any symmetry. And this is the finest invariant, and I believe that this is also not an obstruction to making the symmetry on-site. So if you find that this guy is equal to 0 and this guy is equal to 0, then that seems to be a case where the bulk 3 plus 1D U1 QCA is non-trivial, but it's likely that the boundary one representation is actually on-siteable. So then this gives you an example where the map from like QCA to boundary representations in one higher dimension, that classification is not injective. So you can play around with these numbers, and if you choose two flavors and Q1 equals 1, Q2 equals 3, and then nu1 equals 3, nu2 equals -1, you can see that this guy is 0, but this guy is non-zero. If you choose this combination, then you find that both of these guys are 0. And but these guys are non-trivial, and that might be an example of what I mentioned earlier. Interestingly, if I always insist that these two guys are 0, then that always gives me a Hall conductance that's a multiple of 8, which is consistent with this idea that it's kind of a bosonic integer quantum Hall state with even charged bosons, like charged 2 bosons. Okay, so those are just some examples that we would like to make more rigorous. The problem is that we don't know how to quite rotate the unitary to be on-site, even if these two vanish. So constructing that kind of rotation to try to make it on-site, even though the bulk QCA is presumably non-trivial, is ongoing work. Okay, yeah, so let me just conclude with some outlook. So there's a good understanding of these classifications of locality preserving unitaries and their corresponding symmetry representations in a lot of cases. But especially for continuous symmetries like U1, this is still not fully understood. And we've just shown kind of a partial classification. And there's, as I mentioned on the previous slide, there's possibly a much richer classification. There's something that I would like to prove for interacting systems. So as I mentioned, for the non-interacting single particle setting, one can or non-interacting free fermion setting, one can show rigorously that if you have a integer Hamiltonian with non-trivial Chern number of the bands, then this H can't be strictly local. There's an analogous kind of statement that one would want to prove in interacting settings. In particular, I would want to show that if you have a Hamiltonian, many-body interacting Hamiltonian that has an integer spectrum and has non-trivial Hall conductance on one of the eigenvalues, then it can't be made strictly local. I don't know how to prove this, but this is something I would like to say is true. I should mention that commuting projector Hamiltonians, of course, can have integer spectrum, but it might be the case that integer spectrum is more general than commuting projector Hamiltonian. And then what are the physical implications for the resulting non-onsiteable symmetries if they don't correspond to kind of an anomaly in the usual sense, in the quantum field theory sense? Okay, thank you for your attention and your questions.
Okay, thanks very much, Caroline. Are there more questions? Yes, Yuan.
Want to clarify, so for fermionic QCA or LPU, so what's the rigorous part and what's the conjecture part? Because for the bosonic one, beyond the GMBW index for the translation, all higher dimensional QCA, they are basically just conjecture. Like based on the fact you mentioned, like the commuting projector Hamiltonian and not realize the base with chiral central charge. But for your case, it's not about chiral central charge, it's more about the Chern number. So I think maybe Lucas and Anton, they have more rigorous proof. Like if you have some non-trivial Chern number, it cannot be realized by some commuting projector Hamiltonian. Yeah, so I want to know for many case, whether it's more rigorous than a bosonic QCA.
Okay, so thank you for the question. I think that it's a bit distinct from the QCA that you have in mind because those guys are non-trivial QCA, period. All of the ones I talked about today are non-trivial kind of U1 QCA. So they are only non-trivial if you preserve an on-site U1 symmetry in 3D. And even though we pumped chiral things to the boundary, those are invertible chiral phases. And so that's a bit distinct from these Walker-Wong models, which pump non-invertible phases with ungappable boundary. And so in the case where the phase that you pump to the boundary is actually invertible, you can show that you can write it as a locally generated unitary. In this case, it's just protected by U1 symmetry. So I would say that if you have a bosonic system, there might be kind of classification in the absence of any symmetry. But if you assert additional symmetries, like U1 symmetry, for example, that was not a question that was studied in those papers. Okay, so then in the context of classification with U1 symmetry, I would say that there has not really been conjectured kind of complete classification in fermionic or bosonic sense. Does that answer your question?
Okay, there seems to be maybe an audio problem. Okay, let's continue. Sal.
Thanks for the talk, Caroline. One thing I was wondering is, what do you expect, or rather, what do you expect to say this? Well, I feel like a lot of what you did depended on the local Hilbert space being finite. If you instead had infinite dimensional local Hilbert spaces, do you expect any of this structure to remain, or is it all gone?
Yeah, that's a good question. So the U1 QCA that when you classify U1 QCA in one dimension, we assumed a finite dimensional local Hilbert space because they can presumably be trivialized with infinite dimensional local Hilbert spaces. So now in 3 dimensions as well, one thing that recently thought about in conversation with Wilbur was when we talk about kind of non-onsite symmetries, there's like 2 concepts. One is whether or not we can gauge it, and one is whether or not we can make it on-site. And for finite symmetries, these are kind of equivalent in lattice systems. But now when we talk about U1 symmetry, naturally you would include gauge fields that are infinite dimensional, right? And so it's kind of unnatural to compare it to on-siteability with finite dimensional ancillas. And so then these kinds of on-siteability questions, it might be the case that when you allow gauge, like maybe these U1 symmetries are still gaugeable in some sense because you do allow kind of infinite dimensional gauge fields when you do gauging. So that's also a question that hasn't been completely hashed out, like doing that explicitly and showing that it works. And yeah, so indeed, the nice thing is that in the 1 plus 1D case, the non-trivial classification of U1 QCA is pretty clear how to trivialize it when you have kind of infinite dimensional.
So is it right
but
to expect that all of these anomalous LPUs will become anomaly free if you allow infinite dimensional local Hilbert spaces?
Yeah, I think that's right. In particular, we kind of know how to construct even like commuting Hamiltonians with non-zero Hall conductance. So I think that there should be a construction that trivializes in that kind of Hilbert space. Yeah, thanks for the question.
Thank you.
You okay?
Yeah, I have a question. So, like, there has been some discussion of the like symmetry classification of the symmetry preserving QCA, right? Like, by Sirac or some like classifying MPU preserving some discrete symmetries. And meanwhile, your classification is based on some boundary commutator, like taking truncation of the symmetry operator and unitary and take a commutator and extracting some boundary operator. So does your classification reproduce the Sirac's result on the G-symmetry QCA in 1 plus 1D, or is it different? Do you have a comment about that?
Yeah, so that classification for 1D MPUs, matrix product unitaries, would match with this classification. So that one in 1 plus 1D, really all they get are 1 plus 1D SPT entanglers. So for finite symmetries, like not allowing U1 symmetry, you don't need to use the structure of matrix product unitaries, but you can show that, for example, if I go back, oopsies, if I go back to this guy here, this also just classifies 1D SPT entanglers because this gives you a invariant that classifies 1 plus 1D SPTs. So indeed, for 1 plus 1D,
Like I'm not
I
seeing
don't see anything.
oh, okay. Do you see this?
Yeah.
Okay,
Yeah.
yeah. So this, of course, classifies 1 plus 1D SPTs. So for finite symmetries in 1 plus 1D, that paper that classified matrix product unitaries with some symmetry is consistent with other work, including this work here.
Oh, okay, thanks.
But they didn't, consider higher dimensions or like continuous symmetries.
Okay.
Yeah, they also considered like a strong equivalence in that paper, which means that so the difference between stable equivalence and strong equivalence is what kind of ancilla you're allowed to tensor in. And so in that paper, one of the other things that they did was they also considered MPU's classification with strong equivalence, which means you only allow adding ancillas that carry the same on-site representation of the symmetry rather than any on-site representation of the symmetry. And in that case, they gave that's actually a more complicated story that I don't think has been fully worked out.
I see. Thanks.
Okay, I don't see any more questions. Let's thank Carolyne again.